Hello friends, welcome to the channel Physics by IITians.
Hello friends, this is second lecture of nuclear and particle physics and this is important revision class from Physics by IITians channel. So friends, greetings from our channel that we can guide you for PhD integrated PhD physics with our examination, that is full length test series, subjective test series, as well as our interview guidance. For more, please contact us to this telegram channel or this number or this email ID da@gmail.com, where these all are in small letter. So let's start the video. In this video lecture, we shall basically discuss about liquid drop model. Now, why the nucleus can be thought that this is kind of a liquid drop. Why is it so? So first understand the similarities between a liquid drop and a nucleus. So the liquid drop model of the nucleus was first proposed by Niels Bohr and F. Kalkar in the year 1937. And they observed that there exist many similarities between the drop of a liquid and a nucleus. For instance, like liquid drop and nucleus both possess constant density, and also nucleus has some constant binding energy per nucleon of, and it is similar to the liquid drop having latent heat of vaporization. And evaporation of a drop, this corresponds to the radioactive properties of the nucleus, that is the nuclei can be decayed, okay. And also the condensation of drops, that is suppose there is a condensation of drops, so it is kind of similar with the formation of compound nucleus. So there are much more similarities between a liquid drop and a nucleus. So according to that model, they have proposed some terms that will going to give the nucleus like a liquid drop, and they will account for the binding energy of the nucleus. The first term according to the liquid drop model should be the volume term, that is, so suppose the nucleus is supposed to be a spherical in shape, not it is actually spherical, but for convenience we can suppose it like a spherical shape, and in the stable state it is spherical. So the radius of the nuclei r can be written as r naught a to the power 1/3, as we have seen in the previous lecture, that is lecture 1. So just as a liquid drop is spherical, so nucleus is also spherical. So there will be asymmetrical surface tension forces, and these surface tension effects are analogous to the potential barrier effects on the surface of the nucleus, right? So the density of a liquid drop is independent of the volume, and so the nucleus also, the density of the nuclear density is independent of the type of nucleus. But the dissimilarity is the density of liquid depends on the kind of liquid, such as whether it is a oil or whether it is a water or whether any other liquid. But nucleus kind of independent of its type of nucleus. Now another similarity, like the nucleons inside the nucleus, the molecules in the liquid drop interact only with the nearest or immediate neighbors. And the non-independence of the binding energy per nucleon on the number of nucleons in the nucleus is analogous to the non-independence of heat of vaporization of a liquid drop on the size of the drop. So another many more similarities, if we kind the similarities of the evaporation with the analogous to the compound nucleus, and also phenomena of nuclear fission is kind of the splitting of the liquid drop into two or more parts. So these are kind of similarities between the nucleus and liquid drop. So after considering these effects, they proposed a semi-empirical binding energy or mass formula, and the proposal was given by Weizsäcker, a German physicist, and this, according to him, the semi-empirical formula for the nuclear binding energy in mega electron volt for the nucleus Za, where Z is the atomic number, A is the mass number. It will account for the volume energy term, it will account for the surface energy term, a Coulombic term, asymmetry term, parity term. So the binding energy is AV into A minus AS A to the power 2/3 minus AC into Z minus 1 by A to the power 1/3 minus AN into A minus 2Z whole square divided by A plus delta by a to the power 3 by 4. So I shall explain term by term meaning of this. So know the values of this constant, that is AV is 15.75, AS is 17.80, AC is 0.71, AN is 22.7, delta is 33.6, are all in mega electron volt. The book I am following is H.N. Ghoshal Nuclear Physics book. So the first term, that is the volume energy term, that is EV equals to AVA. So this is the volume effect, that is representing the volume energy of all the nucleus. And since it is the binding, it is the going to contribute to the binding of that nucleus, so the term will be positive. And how is it so? Because volume is proportional to R cube. Now R is proportional to a to the power 1/3, so R cube will be proportional to A, so the volume energy term will be proportional to A, and the proportionality constant is AV. Okay, alright. So AV equals to AV into A, and this energy corresponds to the amount of heat energy, like the heat of vaporization required to transform a liquid to its vapor state, being proportional to the mass of the liquid. Just if you want to have some analogy between the volume energy of a nucleus and the volume energy of or heat energy for the liquid. The second term we should account, that is the surface energy term, and this surface energy term like a effect of surface tension. Since we assume that the nucleus is kind of spherical, so there should be some surface tension, and what should be the term? This should be the term correspond to the surface energy ES, and surface energy should be proportional to the surface area of the nucleus, that is 4 pi r square. So ES, that is the surface energy term, is directly proportional to r square. Now r square term you have to account here, so r square is directly proportional to a to the power 2/3. So ES is proportional to a to the power 2/3, as R is proportional to a to the power 1/3. So ES is proportional to a to the power 2/3. The proportionality constant is small as. So the second term, that is the surface energy term, has become ES equals to AS into A to the power 2/3. Third term is the Coulomb energy, because nucleus there are charged particles, the protons, so we have to account for the interaction between the protons, that is the Coulombic interaction or Coulomb electrostatic repulsion between the charged particles in the nucleus. And what will going to do it? It will be actually repel, so it will not contribute to the binding energy, rather it kind of a negative term to the binding energy. So we have to, first of all, we have to know what are the combinations for a given proton number Z. So that will become Z into Z minus 1 divided by 2. So the energy of interaction between the protons is inversely proportional to the separation of their distance R. So the Coulombic repulsion we should account, that is EC equals to K into Z minus 1 divided by R. And R is R naught e to the power 1/3. So this term can be rewritten as AC into Z minus 1 divided by a to the power 1/3. And this is a negative quantity because it is not going to contribute, because it is repulsive energy. So the term, that is E Coulomb, has come directly here from the Coulombic repulsion. Next term is the asymmetry term. Asymmetry term means, suppose we have seen in our binding fraction curve also, if n equals to Z, that is number of neutrons is equal to number of protons, then the nucleus are stable. Like the lighter nuclei, suppose we are taking the oxygen, 8 is the proton number, 8 is the neutron number. Suppose we are taking the carbon atom, 6 is the proton number, 6 is the neutron number. So these are kind of lighter nuclei, are kind of stable nuclei. But as we go increase the mass number, that is A increases, the symmetry of the proton and the neutron number is lost, and we get that there are more number of neutrons than the protons to maintain the nuclear stability. So this excess number of neutrons over protons, that is n minus Z term, is the measure of the asymmetry, and it actually decreases the stability of the binding energy of this medium of heavy nuclei, because as the nucleus is getting heavier, it is much more going to be low stable, not full like lighter atom, they are much more stable than the heavier atom. So this term actually is going to give the asymmetry in the number of the neutrons and protons. So you have to account the difference between the neutron number and proton number. So EA is proportional to n minus z, or EA can be written as n minus z into A, or EA can be written as AN into n minus z whole square divided by A, or AN A minus 2z whole square divided by A. So this term is asymmetric energy term, and this is a negative term also. Next is the pairing energy term. So this is actually purely a corrective term here, nothing more than that. So this pairing energy term EP can be written as plus minus delta by A to the power 3 by 4. So if Z is even, N is even, then A will be also even. If Z, that is the atomic number, is even, proton number is odd, then mass number A is odd. If any of the Z and N is even and odd, then it will be odd. But if both are odd or even, then it will give you even. So these terms, that is even odd combination, will give you EP term as 0. Even combination will give the EP term as plus delta by A to the power 3 by 4. Odd term will give the EP as minus delta by A to the power 3 by 4. So let's have look in the in a formula for the binding fraction. So binding fraction Fp equals to binding energy per nucleon. So it can be written as Av. Last time it was Av into A. So Av by A into A, that will only term, remaining term is AV, minus AS by A to the power 1/3 minus AC into Z minus 1 by A to the power 4 by 3 minus AN into A minus 2Z by whole square divided by A square plus minus delta by A to the power 7 by 4. So in the previous formula, that is this formula, you have to only divide it by A term, and that's you will get that binding fraction. Okay, then you will get this formula. Now let us have a look about the mass of the nucleus to find out that what is the atomic number or what is the proton number for which we will get the highest stable nuclei or the most stable nuclei. So let us calculate for the formula for the mass of the nucleus. So mass of the nucleus, that is ZMA, is the mass of the constituents minus binding energy, that is Be by C square. So mass of the constituents is mass of proton ZMP plus mass of neutron, means A minus Z into Mn minus Be by C square. So right here the binding energy by C square term. So you will get ZMP plus A minus ZMn minus 1 by C square into the binding energy term which we have got from the same empirical mass formula. So this above formula is known as, which we got from the liquid draw model. So this mass formula is known as the semi-empirical mass formula. So you have to remember this one. Now suppose we assume some terms here as Fa, for this term, this much amount of term, then we will get that semi-empirical mass formula MAZ can be written as Fa plus Pz plus Qz square. Where we taken this term from this formula, we have kind of, this is constant term which is independent of Z. We have taken it as Fa, and we have collected those terms which are dependent on only Z term, and this one, and we give the name as P into Z, and then Z square term we have collected and we give the name as Q, and we get Q into Z square. So mass Az is Fa plus Pz plus Qz square. Now the most stable nuclei for which del m by del z should be 0. So del m by z del z, it will give you P plus 2Qz equals to 0 at Z equals to Za. So Za equals to A by 1.98 plus 0.015 e to the power 2/3. So it will give the stable nuclei. This is the formula for the stable nuclei if we assume nucleus to be a liquid drop. So whenever Z is nearest to this ZA value, we will tell that that nucleus is the actual most stable nucleus for that given A. So free test link is already provided in our portal. You can go to this link, that is https:/remoteeducation.in/physics-by-IITians/index.php. You can give a free test to check yourself, and full solutions are available after the test. Now, we will discuss more problems at the end of this lecture. Let us first understand the theory part. That after the liquid drop model, there are actually some problem that cannot be explained by the liquid drop model. We have to consider some other models like shell model. Now, what is a shell model? Just like the electrons are staying inside different cells, right? In an atom, you have to consider for S, P, D, F, and they are what? They are basically nothing but shells. Now, like inert gases, they are complete. They form complete shells. They form like 8, 18. So just like the inert gas cases, scientists also find out that there are some number of nucleus which are most stable compared to their nearer other nuclei. So they cannot actually explain this from the liquid drop model. So the stability of the nuclei, or rather the chemical stability of the closed electron subshells and shells in the atom, and this similar to the stable nuclear configuration, and physicists inquired if nucleons too form like a similar closed subshells and shells in the nuclei, that is if protons and neutrons in the nucleus are also arranged in some type of a shell structure. Just like electrons, the protons and neutrons are also arranged just like the inner shell, and those shells which are complete, they will form the stable nucleus, and those numbers are called the magic numbers. So the points in favor of shell model, that is just like the inert gas having electrons 2, 10, 18, 36, 54, they have closed shells and they show high chemical stability. So the nuclei with 2, 8, 20, 50, 82, 126 nucleus, also the so-called magic numbers of the same kind of either proton or neutron are particularly more stable compared to the other neighbors. And the number of stable isotopes is larger with respect to number of protons and neutrons equal to either of their magic numbers, and this is the biggest group of isotope. This has, suppose there is an example that's Sn, which Z equals to 50, it has 10 stable isotopes. Calcium, that is Z equals to 20, it has 6. The biggest group of isotope is N equals to 82, and then N equals to 50, N equals to 20. So these are kind of evidences that the extra stable configuration for the magic nuclei, and there are some other cause also. So please read this from a book like Nuclear Physics by S.N. Ghoshal book is kind of quite okay for this kind of discussion. This is very clear language, and this is given, and brief discussion also given there. I request you to read from this book. So what are the salient features or assumptions that were taken for the shell model? So in the shell model, so scientists have assumed that each nucleon, suppose there is a proton or there is a neutron, okay, they are considered that each nucleon are considered as a single particle, and they are moving independently of each other in a time average field. That is, if one, suppose I am considering one proton, so it will be moving with the field of a minus 1, because 1 is I have already considered, so the remaining is a minus 1. So it will be moving independently on the field of a minus 1 nucleons, and it is confined to its own orbit, and it is not perturbed by other nucleons. And it has accounted with a Schrodinger model like wave function we have to treat, and all these things we have to calculate that and assume the harmonic oscillator model. We get that the energy En is n plus half h cross omega, where n is the oscillator quantum number. It can be from 0, 1, 2, 3, so that in the harmonic oscillator model all the energy states are equally spaced, and the wave function psi has both angular, orbital and the
Okay.
so each nucleon also supposed to have orbital angular momentum, spin angular momentum. So all you have to already, we have discussed in our atomic physics lecture that the J values can have from L plus half to L minus half, and the J is the level J equals to L plus half corresponds to S and L parallel to each other, and J equals to L minus half corresponds to S and L anti-parallel to each other. So this is actually the figure for the nucleus of shells and shells. So look here, you have to remember this, okay, this table, that first of all there is 1s half, then 1p3 by 2, 1p half, then 1d5 by 2, 2s half, 1d3 by 2, 1 f7 by 2, 2p3 by 2. So I kind of remember like this way: sp, pd, sd, fp, FPGG, like this way. And also there is a difference between the electronics energy level, sharp levels, and the nuclei. There is first of all the highest number, then it will go to the lower number. Look here, 3 by 2, then 1 by 2, 5 by 2, then 3 by 2, 7 by 2, then 5 by 2, then 9 by 2. So this is the difference between the electronic shell configuration and the nuclear shell configuration. And in this first shell, that is L equals to 0 shell, the total nucleon can be here 2, then 8, then 20, then 50, 82, 126. So look here. So these are going to give you the magic numbers, okay? So this is actually here discussed that how many numbers are possible in a subshell for the nuclear shell and subshells, which I have already discussed. That for the number 2j plus 1, so we have to consider j equals to 1 by 2. So 2 into half plus 1, that will give you 2. And for if suppose j is 3 by 2, so it will 2 into 3 by 2 plus 1, that is 4. Number of nucleons in these two subshells are then 4. So this the same like the electronic shells, here also the same thing, just you have to understand that there is some differences between the arrangement. And what are the success of shell model? This first success is the stability. It can explain the magic numbers, that in that magic numbers why nucleus are highly stable, and it can also tell you about the high binding energy on that closed subshells. And nuclear isomerism also it can explain. Model provides explanation for the ground state spins, magnetic moments of the nuclei, but in the earlier model, that is the liquid drop model, we did not consider about the spin, about the magnetic moments, okay? So, but there are limitations of the shell model, and the limitation that the model does not predict the correct value of spin quantum number in certain nuclei like sodium, and it cannot also certainly do not fit this model about the stable nuclei hydrogen, lithium, boron, nitrogen, and it cannot explain the observed first excited state in even nuclei at energies much lower than those expected from a single particle excitation. So we need some other model, and this thing we have to consider in the next lecture. So in this model, we have also taken account the quadrupole moment of the nuclei, and this is given as Q, capital Q, that is minus 3 by 5, 2i minus 1 by 2i plus 2 into r square. So in the event Z odd n nucleus, the protons couple to j equals to 0 and neutrons to j equals to jn. So the resultant angular momentum, that is j proton plus j neutron, will become, as j equals to 0 for the proton, it will become j equals to j neutron. And suppose you have odd Z and even n, then j equals to jp. and suppose both the even proton and neutron both are even, then J equals to 0. So the ordered nucleus, now you have to consider, we have already considered the even proton, odd neutron, odd proton, even neutron, even proton, even neutron. Now we are left with odd proton, odd neutron combination. And this ordered nuclides, the angular momentum J is given by Nordheim's rule, and this can be stated this way. That is strong rule and weak rule. Strong rule is Jp is L plus half and Jn is L minus half, or the reverse. Then I equals to mod of Jp minus Jn, and I is J value. And weak rule for J equals to L plus half or both J equals to L minus half, then I is lying in between Jp minus Jn to Jp plus Jn. And also this rule can also be rewritten as, if this n number, that is Jp plus Jn minus Lp minus Ln equals to 0, then I equals to Jp minus Jn, and if n equals to plus minus 1, then I is either Jp minus Jn or Jp plus Jn. And look here, these values are positive as these are mod value. So let us take some example, okay? Then it will be clear for you. So we are taking the order of nuclei case. Here, look here, the nitrogen 716. Z is 7, N is 7. Both are odd. First of all, calculate the configure the shell, atomic nuclear shell, that is 1s half, 1p3 by 2, 1p half. 7 numbers, so here 2, then 4, then 1. So Lp, that is for the proton, Lp is 1 and Jp is half. So P is 1, that is Lp is 1. For p orbit, Lp is 1 and J is half, okay? And N, that is for the neutron, consider the number of neutron is N. This N is nitrogen, this N is the neutron number, okay? So for N, you will arrange 1 is half, 1p3 by 2, 1p half, 1d5 by 2. And for D, L equals to 2 and F equals to 5 by 2. So calculate the value of N number. This N is this N, okay? So this N is Jp plus Jn minus Lp minus Ln. So Jp plus Jn minus Lp minus Ln. Jp is plus half, Jn is plus 5 by 2, Lp is 1, Ln is 2, and it will give you 0. So whenever N is 0, what is I? I is mod of Jp minus Jn. So J value, that is the I value, that is the angular momentum value, is given as half minus 5 by 2. It is a mod value, so it is a positive number, so plus 2. Suppose let us take some other examples. So find out the ground state spin and parity of zinc 3067 nuclei. So first of all, know about the number of protons, know about the number of neutrons. So the number of protons is 30, number of neutron is 37. So the one unpaired neutron is present here and it will contribute for the ground state spin and parity. So configure it, that is 1s half, 1p3 by 2, 1p half, 1d5 by 2, 2s half, 1d3 by 2, 1f7 by 2, 2p3 by 2, 1f5 by 2, it is 5. So the ground state spin is L equals to 5 by 2 and parity is minus 1 to the power 3 because this is F. So S, P, D, F. Now this is 3. So this is minus 1. So spin is 5 by 2, parity is minus 1. In the next lecture, we shall know about the collective model and let us briefly discuss some more problems that has already come in NetGate paper. Predict these ground state spins and parities and the magic moments of aluminium, sulfur, argon. So aluminium 1327. First proton number is 13, neutron number is 14. So we have to consider the proton number because odd number of protons here present. So configure it 1 is half, 1p3 by 2, 1p half, 1d5 by 2. So J equals to 5 by 2 and d is L equals to 2 for the d orbit. So the purity is minus 1 to the power L, that is minus 1 whole square, it will become plus 1. So even purity 5 by 2 plus 1. For sulfur 1633, here proton number is even, neutron number is odd. Account for the neutron and find out the J value. Here J value is 3 by 2 and L equals to 2. So purity is minus 1 to the power L or plus 1. So 3 by 2 plus or 3 by 2 even purity. If you account for the argon 1841, so proton value is 18, that is the even number, 23 is the neutron value, so you have to consider for the neutron value, and it will become J equals to 7 by 2 and L for F equals to L equals to 3, so minus 1 cube, that is minus 1, so it will give odd purity. Okay, so friends, I think you understand. It is your homework that here find the total angular momentum and purity for the ground state of sulfur 1633 nucleus using the shell model, and you have to find out the ground J value and the purity. Okay. Here another question, that this sulfur 1633, its electric quadrupole moment calculate from the collective model. So in the next lecture we shall learn about the collective model. And here another question, that find the total angular momentum and the ground state of sulfur nucleus using the shell model, and it is already discussed. So thank you for watching this video. So contact us on our Telegram channel for mock interviews or test series. Full length test series are activated, subject wise test series are activated, and thank you so much. Please, if you like this video, watch this video. Here, look here, there are some important questions that has already come from liquid drop model, that if you find out how do you calculate the binding energy of calcium, that is 2040, the atomic number is 20, mass number is 40, using the semi-empirical binding energy formula. So first of all, you know the binding energy formula, that is Be equals to AV to the power 2/3 minus AC into Z minus 1 by to the power 1/3 minus N into A minus 2Z whole square by A plus delta e to the power minus 3 by 4. Now friends, the AV, AC, AS values will be given in the examination hall. Don't worry for the AV, AS, AC values, okay? You have to only remember the terms, that is the present binding energy term. So calculate this and you will get binding energy as 339.64 MeV. So another question, and this is very important question, show by way of computation which nuclei you would like to be more stable, whether lithium 37 or lithium 38, beryllium 49 or beryllium 410. So you have to consider this formula, that is for a given mass number A, the atomic number Z, the most stable nucleus having Z is A by 2 plus 0.015 A to the power 2/3. So let us take the first one, that is A is 7. So Z will become 3.4. Let us take the second one. A is 8, Z is 3.88. Now compare these two values. For the first one, the lithium, Z value is 3.4. For the second one, Z value is 3.88. But nearer value to 3 is 3.4. So lithium 37 nuclei is the stable nuclei. Let us take this example, that is beryllium 49, beryllium 410. Calculate Z value for A equals to 9, for A equals to 10. For A equals to 9 you get 4.36, for A equals to 10 you get 4.80. Now compare these two values, and 4.36 is nearer to 4. So beryllium 49 nucleus is more stable. So the nuclei having nearly this 4, that is the atomic number is near to this number, 4.36 is nearer to 4, right? So this nucleus is more stable. So thank you for watching this video. So we believe the sharing of knowledge is the best way of helping the society. Hopefully you will also do that. And thanks for watching this video. Please do like this video, subscribe to our channel, join our Telegram channel for daily quiz updates and research articles. Join our FB page, Physics by IITians. Thank you.